Hi everybody, I hope this video finds you well. In today's video, we're going to continue our investigation into basic probability by looking at a couple of examples with slightly more complicated probability situations, where our main goal will be to start by trying to build probability models for each of these situations, and then using those probability models to calculate some probabilities of different events. So let's jump right in and take a look at this example here. So we're going to suppose that we have this bag full of marbles, and inside the bag you have 6 blue marbles, 8 red, 6 green, 4 purple, and 5 yellow. It's probably beneficial if we see something like this to probably want to know how many there are in total. So adding these together real quick, we can see that there's 6, 14, 20, 24, and 29 marbles overall. So we know that there's 29 marbles in that bag overall. We're going to go ahead and suppose that you pull out one marble at random. So you select one of these 29 and you decide to record its color. So the important characteristic here is the color of the marble you choose. So what we want to do is, in part A, we'd like to write out a probability model for this probability experiment. So in other words, we want to list out the outcomes and their associated probabilities. And then in B and C, we'll calculate the probability of a couple events here. So let's go ahead and start with this probability model. Remember, a probability model is a list of the outcomes, all the things that can happen, along with their associated probabilities. Now, as we discussed in the previous video, sometimes there are several different ways to sort of see or understand what are the list of outcomes, what is the sample space. But keep in mind here that it says specifically here that we're interested in recording its color. So we know that that means that the outcomes we should be looking at are the different colors here. So the outcomes are the blue, red, green, purple, and yellow. All right, those are the 5 possible outcomes in this situation. You can get blue, red, green, purple, or yellow. So those are our outcomes. Now, as we discussed in the previous video, we have to be very careful with the probabilities here. There are 5 different outcomes, but we cannot say that they are equally likely. The chance that we get blue is not necessarily the same as red, or green, or purple, or yellow. Why is that? Because there's a different amount of each marble of each color in the bag. Each marble, each of the 29 is equally likely, but that doesn't make each color equally likely. So how can we figure out the probabilities? Well, we simply look at how many there are of each color out of the total of 29. Because remember, the 29 marbles are all equally likely. The colors might not be, but the individual marbles are. So the chance that we get blue must be that there are 6 blue ones out of the 29 overall. So we'd say that that probability is 6 out of 29. For red, we know that there are 8 red, and there's 29 overall, so 8 out of 29. For green, there are 6 green out of 29 overall, so 6 out of 29. For purple, out of 29 overall, so 4 out of 29. And finally, 5 yellow out of the 29 overall, so 5 out of 29. Now, let's take a look at a couple things with this. Remember, there were 2 things that we had to make sure for every probability model, so they can be sort of used as a check here to make sure that we did this correctly. Remember, all of these probabilities need to be between 0 and 1. Well, that's definitely the case. There are no negative numbers here, and none of them have a numerator larger than their denominator, so that means they're all going to be less than 1. We can also check that we did things correctly by checking the second rule of probability models. Remember, the second rule is that the probabilities have to add up to 1. So if we check here, 6 plus 8 is 14, plus 6 is 20, plus 4 is 24, plus 5 is 29. 29 out of 29 is indeed 1. So that sort of confirms that this really is a probability model. Now, you don't have to check those things, because if you build the model correctly, then those things are guaranteed to be true. But if you want, especially summing up the probabilities is just a good check to make sure you didn't accidentally miswrite anything or miss anything there. All right, now we're going to calculate some probabilities using this model. So for B, we'd like to get the probability that we get yellow or red. Okay, so the event that we're looking for is that the marble comes out yellow or it's red. We don't care which one, as long as it's either yellow or red here. So, as we've sort of seen several times in our class thus far, this OR generally indicates that we should be adding together, because we don't care if it's yellow or red. So we can simply add together the probability that it was yellow, which is 5 out of 29, with the probability that it's red, which is 8 out of 29. So we can do that. That would be 5 out of 29 plus 8 out of 29. Notice that since we are adding fractions with the same denominator, we can just add the numerators together, and we get 13 out of 29. Notice this also makes sense if you just think about it from a fundamentals perspective. If you're just saying you want yellow or red, and you just go back up here, well, there were 8 red ones, 5 yellow ones. That's 13 marbles overall that satisfy being either red or yellow. 13 out of 29. That's exactly the answer we got here. All right, let's go ahead and calculate another probability. Probability that we do not get a purple, so not purple. So for whatever reason in this event we're trying to avoid purple. Well, you can imagine there might be sort of 2 ways to do this. You can sort of think about not being purple as being either blue, red, green, or yellow. So we can add those together. So we can say 6 out of 29 that it's blue, 8 out of 29 that it's red, 6 out of 29 that it's green, and 5 out of 29 that it's yellow. That avoids the purple. Adding those together, we get 25 out of 29. So we get the probability that it's not purple is 25 out of 29. Of course, we could just do that from back here. If we say, okay, get rid of the purple ones, then we've got 6, 8, 6 again, so that's 20 overall, plus those 5, that's 25. Yep, 25 out of 29. Now, later on, as we get further into our investigation of probability, we'll start to introduce some probability rules. And one of those probability rules is something called the complement rule. And the complement rule gives us a very clever way of doing this. We could sort of simply notice that there were 4 purple, and if we do 29 minus 4, we immediately get that 25. So we'll be able to sort of do questions like this using a much fancier rule later on that can make things a little bit quicker. But notice that even though we haven't discussed that rule yet, we're still able to do it just sort of directly by brute force, by adding up everything that was not purple and getting that 25 out of 29. Okay, so this was our first example here. We took a sort of probability situation where we're looking at these different colors. The colors were not equally likely, so we went ahead and built a probability model. It wasn't super difficult to do that because there were just 29 marbles and the numerator was always just how many of each color, and then we calculated a couple probabilities from this. All right, let's continue on with another example where building the probability model will take a little bit more effort, at least in terms of organizing the different possibilities. All right, so for this example, we're going to suppose you're playing a game. In this game, you roll an 8-sided die, so not a standard 6-sided die, but an 8-sided die, and it's labeled 1 through 8. And you also flip a coin. So in this game, you get to roll the dice and you flip the coin. The rules are, if you get heads, you record double the number you rolled on the dice. So that means if you roll like a 5 and the coin comes up as heads, you would count that as double 5, so 10 overall. If you get tails, you record the number you roll without changing. So if you roll a 3 and get tails, you just count that as a 3. So you double on heads, you don't do anything different on tails. What we'd like to do is write out a probability model, just like we've done in the past here, and then use that to calculate some probabilities here. All right, so what makes this different? Well, not too much, except that it might be a little bit harder to think of all the different outcomes here, because we've got this dice and this coin, but ultimately we don't care about what happens only on the dice or only on the coin. We sort of happen to care about the result, whether or not the number has been doubled, or what number it is after we don't double it, or whatever. So the easiest way to deal with situations like this, if you guys ever encounter something where you're doing 2 things, like rolling a dice and flipping a coin, or rolling 2 dice, or different things like that, is to sort of draw a little chart or table to organize everything. So let's go ahead and do that. Let's put our 8-sided dice here, and go 1, 2, 3, 4, 5, 6, 7, 8. Those are all the possibilities that can show up on the dice. And let's put the coin over here, which can be heads or tails. And then on the inside of this chart, so notice that all this stuff up here is what happens on the dice, all the stuff over here is what happens on the coin, and we're going to fill in the inside of this with the actual result of the game, or the result under these rules. So let's see. If we get heads on the coin and 1 on the dice, well, we know that if you get heads, you double the number you rolled. So doubling 1 means that the result here would be 2. If you get heads on the coin and you get a 2 on the dice, you would double that and count it as a 4. Heads on this coin and 3 on the dice, you double it and get 6, 8, 10, 12, 14, and 16. Notice all of those, the actual results are double what you got on the dice, because for all of these we're assuming you got heads on the coin. For tails, remember you don't change anything. So for tails and a roll of 1, that would count as 1. For tails and a roll of 2, that would count as 2, 3, 4, 5, 6, 7, 8. So why is this sort of useful? Well, it helps organize all the possibilities. We can now see that the results of this game can be 1, 2, 3, 4, 5, 6, 7, 8, as well as 10, 12, 14, or 16. So those are all the possible outcomes. So we can make use of this in terms of writing out our model. So our actual model. Keep in mind, just in terms of the language or the terminology, this right here is not the model. This is just an organizational technique. The model is, of course, the outcomes with the probabilities. So what are the possible outcomes here? Well, anything that's sort of unique in here is an outcome. So that means 1, 2, 3, like we said, 4, 5, 6, 7, 8. Notice that 9 is not possible. There's no 9s that show up in there. So we can just skip to 10, 12, 14, and 16. So the outcomes when you play this game are that you could end up with a 1, 2, 3, 4, 5, 6, 7, 8, or a 10, 12, 14, or 16. How do we calculate these probabilities? Well, notice that this is the total number of outcomes, and if we just count that up there, pretty easy to do so. We can just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we've got 16 total here. So that means everything's going to be out of 16, because any of these 16 possibilities are all equally likely, because they each result from one thing on the coin, one thing on the dice. So how many ways are there to get 1? No, there's only one way, so the probability there would be 1 out of 16. For 2, notice that it can happen here or here. In other words, it can result from heads and 1 or tails and 2. So that would be 2 out of 16. For 3, it can only happen here, which would be 1 out of 16. For 4, it could happen here or here. In other words, it can come from tails and 4 or heads and 2. So that's 2 out of 16, 2 ways that that can happen. For 5, there's only one way right there, so 1 out of 16. For 6, there's 2 ways, so 2 out of 16. For 7, there's just one way, so 1 out of 16. For 8, there's 2 ways, so 2 out of 16. And then hopefully we can sort of see that for 10, 12, 14, and 16, there's only one way each. So all the remaining ones should be 1 out of 16, 1 out of 16, 1 out of 16. All right, does this make sense for a probability model? Well, certainly all these are between 0 and 1. And if we add these up, 1, 3, 4, 6, 7, 9, 10, 12, 13, 14, 15, 16. 16 out of 16, okay, it does sum up to 1. So this is our model. These are the outcomes. They're not all equally likely. Things like 2 or 4 or 6 or 8 are easier to achieve because for each of those, there's 2 ways that it can happen. Everything else only has one way of happening. All right, now let's use this to answer a couple questions. So we'd like to calculate the probability. You record an even number. So we'll do that right here. So for part B, we want to get the probability. You get an even number. So which of these outcomes counts as an even number? Well, it'd be the 2, 4, 6, 8, 10, 12, and 16. So this is saying the same as the probability that we get a 2, or a 4, or a 6, or an 8, or 10, 12, 14, 16. So any of those things will satisfy us getting an even number as our result. So we can just add those probabilities together. 2 out of 16 plus 2 out of 16 plus 2 out of 16 plus 2 out of 16. For 2, 4, 6, and 8, those all had 2 out of 16. And then 1 out of 16 for all the remaining ones. So plus 1 out of 16 plus 1 out of 16 plus 1 out of 16 plus 1 out of 16. If we add those all up, they all have the same denominator. Notice that's why we're not like simplifying the 2 out of 16. You guys probably know from like arithmetic, 2 out of 16 could be reduced to like 1/8. There's no reason to do that when working with probabilities, because by keeping the denominators all the same, we're able to easily add them up. So in this case, if we do that, we get 2, 4, 6, 8, 9, 10, 11, 12. So the overall probability is 12 out of 16. In other words, if we went back to the original diagram, 12 of the numbers in here are all even numbers out of 16. And you can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of them are all even numbers. Perfect. Let's try another one. So for part C, we want to calculate the probability you record a number less than 6. So probability less than 6. Which sort of outcomes satisfy being less than 6? Well, it would be things like 1, 2, 3, 4, 5, right? 6 would not count because 6 is not less than 6. So only 1, 2, 3, 4, and 5 would count. What are their probabilities? Well, since we have this nice model here, we can use that. It would be 1 out of 16 plus 2 out of 16 plus 1 out of 16 plus 2 out of 16 plus 1 out of 16. So I'm just recording what each of these probabilities are from here. So we're saying for the 1, it would be 1 out of 16, then 2 out of 16, then 1 out of 16, then 2 out of 16, then 1 out of 16. Just summing all those together. All right, what do we get if we do that? Well, we get 1 and 2 is 3, 4, 6, 7. So the chance that we get a number less than 6 is 7 out of 16. I think we've got one last one to do with this. We want to calculate the probability that you record a number that is at least 6. So for D, at least 6 would mean 6 or above. So that means greater than or equal to 6. So what are the options for that? Well, 6 would do it. 6 is at least 6, as well as 7, 8. We don't need to write 9 because it's not a possible outcome. 10, 12, 14, and 16. All of these things down here are all ways where we would get something that is at least 6 or higher. If we write down those probabilities, for 6, it would be 2 out of 16. So 2 out of 16 plus 1 out of 16 plus 2 out of 16 plus 1 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 out of 16. We add all those together, 2, 3, 5, 6, 7, 8, 9, and we get 9 out of 16. So the chance that we play this game and we end up with a result that is greater than or equal to 6, or aka at least 6, is 9 out of 16. Now, something I just want to call your attention to as we get ready to move into our next topic, like we've mentioned, is introducing some probability rules. It should not be a surprise that this 7 out of 16 and this 9 out of 16 add up to 1. Because notice, right, if for some reason 6 is what we were interested in, getting a number less than 6 and getting a number at least 6 are opposites. Either one or the other has to happen. When you do this, you either get a number less than 6 or you get a number greater than or equal to 6. So of course these probabilities have to add up to 1 because they're opposite or complement events. And again, that's something we're headed to in the next video, where we'll introduce some basic probability rules, including this idea of the complement rule, the opposite of an event. But right now, it should make sense. The opposite of getting a number less than 6 is getting a number greater than or equal to 6. And these probabilities, it's not a coincidence, they add up to 1. Okay, so this example was a little bit more challenging because we had to sort of diagram out all the different options. It's different than what we did back here. Here, all the options were just listed for us, so we just simply counted and put it over the total to build the model. But here, because we're following these rules about this weird thing where you double when you get heads or you leave things the same when you get tails, we had to actually organize it and then create the model. Of course, once we had the model, calculating all these probabilities, pretty easy. All right, let's try this one more time with another example sort of similar to this, using sort of 2 probability generators. Our next example will be 2 dice instead of a dice and a coin, and trying to file some rule that puts them together. So, for this example, which will be our last for this video, we're going to suppose that you're playing a game again. In this game, you roll 2 6-sided dice, so back to standard dice. The dice are both labeled 1 through 6. And then, instead of doing any of this weird doubling, you just simply add the 2 dice together and record their sum. So in other words, this means if you roll like a 2 and a 4, you add them together and it counts as a 6. If you roll a 6 and a 3, you add them together, it counts as a 9. So we're adding the 2 dice together. Once again, the first thing we're going to try to do is come up with a probability model, and then we'll calculate some probabilities using that model. So let's go ahead and start with A. We want to try to organize this. Once again, we have these sort of two things. We want to sort of say what can happen on the first dice, what can happen on the second dice, and then what is the result overall. So let's go ahead and put dice 1 here. And of course that can be 1, 2, 3, 4, 5, and 6. And then let's go ahead and put dice 2 up here. 1, 2, 3, 4, 5, 6. So of course this is everything that can happen on dice 1. This is everything that can happen in dice 2. I like to put those sort of solid lines around this, sort of separating what's going on with each dice individually. And then on the inside of the table, I'm going to put what the result is. So according to the rules of this game, when you get a 1 and 1, you add them together and you get 2. When you get a 1 and a 2, you add them together, you get 3. 4, 5, 6, and 7. Same thing here. If you get a 2 and a 1, you add them together, 3. 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9, 10. 6, 7, 8, 9, 10, and 11. And 7, 8, 9, 10, 11, and 12. So notice that this tells us the lowest outcome is 2. The lowest possible number if we're adding them together is 2 because we get a 1 and 1 and it becomes 2. And the highest one is 12, which comes from 6 and 6, giving us that 12 overall. So all the outcomes are from 2 to 12. Now, something you should just be aware of here is that when we're filling in a table like this, you got to remember that you have to follow whatever the rule of the game was. In this example back here, it was this weird thing about doubling if you got heads and leaving it alone if you got tails. This time we're adding the dice together. So that's why we're getting these values in here that come from summing up each of those numbers. All right, let's actually build our model then. So our model, we need the outcomes and the probabilities. Like we said, the lowest outcome is 2, and it looks like we do have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 through 12 are all possible outcomes. Okay. All right, so there we go. There's all our outcomes. Now let's get the probabilities. We need to know how many things there are in total here. Well, we can go through and count, going like 1, 2, 3, 4, 5, 6, so on. But of course, if you just think about it from like a multiplication standpoint, you've got 6 options here, 6 options here. 6 by 6 gives us 36 options overall, so 36 total. Of course, if you just count them by hand, you'll also arrive at 36. So everything is going to be out of 36. How many ways are there for us to get this 2? Well, only one way, so the probability there would be 1 out of 36. What about for the 3? Well, there'd be a 3 there and a 3 there, so 2 out of 36. For the 4, there'd be 1, 2, 3 different ways that can happen, so 3 out of 36. For the 5, there'd be 1, 2, 3, 4, 4 out of 36. For the 6, there'd be 1, 2, 3, 4, 5, so 5 out of 36. For the 7, there'd be 1, 2, 3, 4, 5, 6 out of 36. For the 8, there'd be 1, 2, 3, 4, 5 out of 36. We probably can sort of see a pattern here. For 9, there's 1, 2, 3, 4 out of 36. For 10, there's 1, 2, 3, so 3 out of 36. For the 11, there's just 2 ways, 2 out of 36. And for the 12, only one way, 1 out of 36. We can check all of these are definitely between 0 and 1, and if we add them up, 1, 3, 6, 10, 15, 21, 26, 30, 33, 35, 36, 36 out of 36. It really is a probability model. Now, what is this really telling us? Well, it's telling us these outcomes are definitely not equally likely, right? Something like a 2 is very rare. To get a 2, you have to get a 1 and a 1. Something like a 7 is the most common because 7 can happen in a bunch of different ways. Something like 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. All of those yield a 7. So a 7 is much easier to get than a 2 is in this situation. So that's what this probability model is telling us. All right, let's use this model to answer some other questions. So for part B, we want to go ahead and record the probability that we get an odd number. So let's go ahead and see that. Probability an odd. Okay, which of these outcomes are odd numbers? Well, it's things like 3, 5, 7, 9, and 11. So this is the probability that we get something like a 3, a 5, a 7, a 9, and an 11. Let's add those probabilities. So that would be 2 out of 36, 4 out of 36, 6 out of 36, 4 out of 36, and 2 out of 36. So let's add all those together. 2 out of 36, 4 out of 36, 6 out of 36, 4 out of 36, and 2 out of 36. If we add all those together, 2, 6, 12, 16, 18, we would get 18 out of 36. So the chance that we get an odd number, if we roll 2 6-sided dice and then add them together, would be 18 out of 36. Now, if you simplify that, you'll find out that it's 50%, meaning that you've got a 50-50 chance of getting an even or an odd in this game. Now that's sort of interesting because if you go back and look at this question, the chance that you got an even number in this game was not 50-50, right? We might sort of think, oh, half the numbers are even, half are odd, so maybe even and odd is always 50-50. But in this game, evens were much more common, 12 out of 16. Odds would only be 4 out of 16. Why were evens so much more common in this game? It's because part of this game was doubling the result. And remember, anytime you double a number, it's guaranteed to be even. So the structure of this game made evens very, very common. Whereas the structure here of just simply adding numbers together, it makes evens and odds the same likelihood. In this case, if you simplify this, you'd find it as 1/2 or 50%. Okay, let's take a look at some other things for part C. If we go back up, part C, we'd like to calculate the probability we record a number greater than 8. So we want the probability greater than 8. Which of these outcomes are greater than 8? Well, 8 would not be included, but everything above would be. So 9, 10, 11, and 12. So this is the same as 9, 10, 11, and 12. Their corresponding probabilities, 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. So 4 out of 36, 3 out of 36, 2 out of 36, and 1 out of 36. Adding those together, 4 and 3, 7, 9, 10. So it's 10 out of 36. So the chance that we get a number greater than 8, 10 out of 36. Notice, just to make sure we're always remembering what probabilities really mean, this means it's more likely to get an odd number than it is to get a number greater than 8. All right, let's try something else then here. For D, we'd like to get the chance that we record an odd number and a number greater than 8. So let's think about how we would do that. Odd and greater than 8. Now again, remember mathematically, when you say and, you're talking about things that have both these traits. So in other words, we need to think of odd numbers, but they also have to be greater than 8. So all the odd numbers are here, but of course 3, 5, and 7 wouldn't work because they're not greater than 8. So the only outcomes that would satisfy this would be 9 and 11. Those are the only odd numbers that are greater than 8 that are possibilities here. Their probabilities, for 9 it was 4 out of 36, for 11 it was 2 out of 36, so we can put those together. 4 out of 36 plus 2 out of 36 would give us 6 out of 36. All right, we got one last one here, and this will also sort of motivate us for our next sort of major discussion, our next video. Let's calculate the probability you record an odd number or a number greater than 8. So now we want to get the probability that it's odd or greater than 8. Well, let's think how we would do that. Remember, when we have or, we are saying that it can be one, the other, or both. So in other words, we're saying any number that is either odd or greater than 8 will do this. So we know that there's going to be some sort of addition here. So let's think about this. What are all the odd numbers? Well, it would be all the things like 3, 5, 7, 9, 11. What are all the numbers greater than 8? Well, we know it would be 9, but we don't need to list that. That's already been listed. We know 10. We haven't listed that, so we should include that. We know 11 would be greater than 8, but it's already listed, so we don't need to repeat it. and 12. So in other words, the numbers 3, 5, 7, 9, 11, 10, and 12 are all numbers that are either odd, greater than 8, or both. Notice, though, that I was careful not to double count. I didn't list things like 9 and 11 twice because they were odd and they were greater than 8. So we have to be careful about double counting. That's something we encountered when we were doing conditional analysis as well. For now, though, we can go ahead and put all this stuff together. So that would be 2 out of 36 plus 4 out of 36 plus 6 out of 36 plus 4 out of 36 plus 2 out of 36. Then for the 10, that would be 3 out of 36. And then for the 12, that would be 1 out of 36 plus 1 out of 36. And if we put all that together, what do we get? 2, 6, 12, 16, 18, 21, 22. So we get 22 out of 36. All right, so we sort of said that this last part might motivate our sort of next discussion. Well, it turns out, as we sort of said, our next big goal is, now that we've gotten some examples of basic probability done, we'd like to start introducing some rules that allow us to sort of calculate probabilities without always having to just, by scratch, look for every outcome and their probabilities and put them all together. Notice that this probability here can actually be found from these here. If we take the probability of odd, 18 out of 36, and we add the probability of greater than 10, 18 plus 10, we get 28. But remember, we said that there would be some double counting because things like 9 and 11 were here and they were here. That's exactly what we measured with the and. So if we take this plus this minus this, 18, 20, that's 28, minus 6, that gives us 22 out of 36. And that turns out to be what's called the addition rule for probability, something that we will define and look at further examples of in our next video.